In this tutorial, I'm going to talk about two parallel derivations, one that you've seen before for electrostatics and one that's very important for our discussion in class for electrodynamics. And they have to do with potentials. You've heard that electric field can be written in electrostatics as a potential. That's called voltage. And let's just remember how that came about. So that starts with the fact that Maxwell's equations say that the curl of the electric field is not in general zero, but if the time derivative of the magnetic field is zero, then the curl of E is zero everywhere in space. So in electrostatics, that's going to turn out to mean that there's a potential. Now the curl of E being zero, we write that as mathematically with the del operator. The curl of the electric field equals zero everywhere. Now why does that mean that there's a potential, a voltage? Well, if the curl of E is zero everywhere, then that means something important about an arbitrary path that we could draw. Here's some path that we could trace out in space, and we could integrate the electric field everywhere along that space. Specifically, we could calculate the circulation of the electric field. And what the curl of E being zero means that along a closed path, it means that the integral of E dot dl equals zero. Now why is that true? Because Stokes Theorem says that the integral of E dot dl is equal to the area integral of the curl of E evaluated everywhere in any surface bounded by this path. And since that surface area integral, the integrand will be del cross E everywhere, and the curl of E is zero everywhere, that's got to add to zero, so E dot dl equals zero. And in English, we would say that the circulation of E is zero along that path. Okay, so if that's true, we can now think about 2 points on this path, 2 points in space, A and B. And we can now think about integrating along an open path from A to B. We can think about integrating what is E dot dl, the same quantity that when we have a closed loop we call it circulation. We integrate a path integral E dot dl along an open path from A to B. And since the integral along any path from A to B and then back from B to A, for any pair of paths, that integral has got to equal zero. That means that any way I get from A to B, it doesn't matter what path I take, because any two paths, their integrals, when I flip the sign of one, they cancel out and give you a zero. So the integral along that open path, that's got to be path independent That sounds like a potential. That's what potentials mean, that the potential only depends upon one point in space relative to another point in space. It doesn't matter how you got from A to B. You have the same change in potential, change in voltage, you would say, regardless of how you get from A to B. That's in fact what it means to have a voltage. What are some other ways of thinking about how we'd write that? We could say that only values at the endpoints affect the integral. So this is a special type of integral whose value only depends upon the endpoints, not upon the path you take. And that means that this has got to equal something like this. It's got to have the flavor of phi b minus phi a. To be absolutely technical, in this derivation there's going to be a minus sign in front of that, but that's not that important. And that's actually the definition of a potential, that this integral of some vector quantity along a path only depends upon the difference in some scalar field's values at the two endpoints. This then is that scalar field. This is the voltage. And if we write it out more, another way of writing this out is to say it's the integral from A to B of the quantity negative grad psi. The gradient of psi is a vector field, dl, that's supposed to be. So now I've got two integrals along the path, along an arbitrary path from A to B, E dot dl and negative grad psi dot dl. And since this is true for any path, this integral and this integral, since they're equal along any path, these integrands must be equal. So therefore, we would say that fields with no curl anywhere can always be written as the gradient or the grad of a scalar field, which we are calling in this case psi. So we end up with the observation that the electric field E, I'll say ES here for electrostatic, ES as a function of position can always be written as the negative gradient of a scalar potential, which we call psi. Now we move on to the second half of the derivation, the one that we actually care about. You all knew that there was such a thing as a scalar potential for gravity or for electrostatic fields, where that's vector potential. That's potential is usually called a voltage. Electrodynamics, the magnetic field can always be written as the curl of a vector potential, but that's not as obvious. Let's set up the parallel discussion. So the mathematical expression that div B is everywhere 0, which is a Maxwell law, which is always true, not just when things are static, that would be that del dot B equals 0 everywhere. Now, instead of thinking about a path in space, like a wire in space, I can think about some volume in space. And I'm just drawing some arbitrary thing now. It's hard to tell this is different from this, but again, this is a path, and this is a three-dimensional. I'll write a V here to emphasize that this is a volume. And this volume here, so for any enclosed volume, we can now assert that the surface area integral of B dot d sigma, that is to say the magnetic field poking through the surface everywhere, that equals 0. You can see how parallel this is to E dot dl being 0 along this closed path. Now you have B dot d area along the surface of this enclosed volume. And we even have a name for that. We would say that the flux, in this case of magnetic field, the flux of magnetic field through that surface equals 0. Again, very parallel to the other derivation. Okay, just like we broke that wire into path from a point A to a point B and back again, we can also think about some surface. Here I'll draw a little loop of wire cutting that volume into two pieces. That's some path P, if I give it a direction like this. I can now think about the integral the open integral, the flux of magnetic field through an open surface bounded by P. And here's two examples of some open surfaces that I could have. I could consider this surface here. I could consider this surface here. I'll call that S2, S1. These are sort of on opposite sides of this edge thing here. But these are just two soap bubbles I could blow along this wire. I could blow any other soap bubble I want. So any surface bounded by that path P could be an open surface for which I could calculate this flux integral. Now, the fact that the flux over the total surface is 0 means that if I add the flux through S1 to the flux through S2, I have to get 0. The point is that it's very parallel to this here, that any surface that I blow a soap bubble with, defined by this area along this path defined by P, that's going to be surface independent. Surface independent. So that means that only now I'm going to write this out, the circulation along the path affects the integral. So we're in a slightly higher dimension here than we were before, but the logic is sort of the same, that the only thing that can affect this area integral, the surface area integral, can be how something behaves right along this edge path. It's the only thing that all of those surfaces have in common, just like the only thing that all these possible paths from A to B have in common are the endpoints A and B. The only thing that all of these possible surface integrals have in common is their edge path P. So the only thing that can affect this integral can be the way some vector field points along that path. So now I'll come down here, very parallel to before, and I'll say that this surface integral has got to equal a closed path integral along path P of how some field points along this path. So only the vector components along the path. So just like I introduced some psi here and said that it's psi at the two special endpoints, here it's some vector A, and only the components of A that point along the path can possibly be important. This is the assertion that there is a vector potential related to B. And if I now think about Stokes' theorem, an integral, a closed line integral of some vector field A is equal to the curl of that same vector field integrated over any surface bounded by that path P. Now you see I have two surface integrals. One is B dot d sigma, one is curl of A dot d sigma. Parallel reasoning with over here says that these integrands must be equal. So therefore, a field with no div anywhere, like B, must always be able to be written as the curl of a vector field. This time I won't write that out in English, I've just said it. So what I'm saying there is that the magnetic field at any position r has got to be, and in fact I'll even include time t, has got to be equal to the curl of some vector potential evaluated at a time a and t. And that is the conclusion that we wanted to defend, that a magnetic field because it has div b of 0 everywhere, can always be written in this class as the curl of a vector potential. QED. That's what we wanted to prove.